So Newton's method is a method for approximating roots of equations. We've got some function, some continuous function f, and we want to solve that equation. Solve this for x. We've seen that you can solve for x with the bisection method. Newton's method is better. What's the basic idea? Here's your graph. There's your root. Call the root p. We have some initial guess, like always. Call it p sub 0. The idea of Newton's method can be described graphically. Now, the book describes it symbolically. We'll talk about that next time that we meet. But it's nice to think about this graphically. We go up to the graph of f, and notice that if I follow the tangent line to the graph of f at that point down to the x-axis, we're practically at the root. This x-intercept for that tangent line is the next value of p. You can see, at least for this visual example, it's going to be pretty close to p. And then you repeat that process. And we're already so close to p that it's difficult to draw anymore. But in reality, you would do the exact same thing. You would go up to the graph, find the tangent line at this point, and find the x-intercept of the tangent line, call that p2. And this will work even if p0 is to the left of p and your graph is below the axis. Although in this case where the graph happens to be concave up, if I follow this tangent line like this and find its x-intercept, the next value of p is going to actually be to the right of p. P1 will be to the right of p. If it were concave down, then it would be to the left still. So that's the basic idea. What do we do with this? We want to take this picture and translate it into some recursive equation that we can iterate. Some function g that we can iterate with our usual iteration scheme. Let's think of it in terms of solving for p1 in terms of p0, but in general, you'll solve for pn in terms of pn minus 1. We would need the equation of the tangent line here, wouldn't we? What's the equation of that tangent line? Well, it would be y equals the initial value of the function at p0, f of p0, plus the slope of the line, which will be the derivative, f prime of p0, times x minus p0. Right? This expression here represents what you could call the local linearization of the function. The function that's nonlinear, the green function f, at the point x equals p0. This could be used to approximate the function f, but what I'm doing now is I'm trying to find this x-intercept. So now set y equal to 0 and solve for x. And that value of x will be the value of p1. So we get 0 equals f of p0 plus f prime of p0 times x minus p0. Trying to solve for x, so subtract f of p0 from both sides to get this. Next, divide both sides by the derivative, f prime of p0, assuming it's non-zero, right? We're implicitly assuming that if we write this, assuming f prime of p0 is non-zero, so that if we happen to choose a p0 where f prime was 0, that would be trouble for this method, wouldn't it? Almost done. Solve for x. So that means x, which is going to be our value of p1, can now be found by adding p0 to both sides and get p0 minus f of p0 divided by f prime of p0. So that's how to get p1 in terms of p0. The general case is the exact same procedure. So in general, p sub n is going to be p sub n minus 1 minus f of p sub n minus 1 divided by f prime of p sub n minus 1. That's how it's traditionally written. Of course, you could get a common denominator of f prime of pn minus 1. You could also write this as p sub n minus 1 times f prime of p sub n minus 1 minus f of p sub n minus 1, all divided by f prime of p sub n minus 1. But it seems simpler to just focus on it in this way and not bother subtracting the fractions. Okay. So let's do a basic application of this. Let's say we want to estimate the square root of 2. Example here, estimate square root of 2 with Newton's method. What do you think I should use for my function f? Got a guess? Root 2 minus x or x minus root 2. That's one possibility. There is a difficulty, you might say, with that, in that you're using root 2 itself in the function, which is what you're trying to approximate. How about a second degree? It would be simpler to go with x squared minus 2. The positive solution of x squared minus 2 equals 0 is the same as the positive solution of x squared equals 2 is square root of 2. We're after the positive solution. Of course, negative square root of 2 is another solution. Of course, we had to prove square root of 2 existed back a week and a half ago, or was it 2 weeks ago? I forgot. That required the intermediate value theorem, which in turn required understanding limits and continuity from real analysis. We didn't really prove it from scratch. So in doing this, we're assuming square root of 2 exists, and it does exist, okay? So we're going to need to use this formula. We need the derivative. It's 2x. And let's go ahead and write how this formula simplifies. Then for this example, p sub n will be p sub n minus 1 minus, okay, f of p sub n minus 1 will be p sub n minus 1 squared minus 2. And f prime of p sub n minus 1 will be 2 times p sub n minus 1. Okay, so that's the recursive formula to use. With a calculator, we can use the ANS feature to do this. Give an initial guess. Now, of course, we know it's close to 1.4, but let's not go too close just for extra emphasis. Let's go ahead and start with 2 as our value p sub 0. Take the previous answer. That's p sub n minus 1. Subtract, careful with parentheses, p sub n minus 1 squared minus 2 divided by 2 times p sub n minus 1, 2 times the previous answer. That'll be p sub 1, 1.5. Here's p sub 2, 1.416 repeating. You could write these numbers down if you like. P sub 0 is 2, P sub 1 is 1.5, P sub 2 is 1.416 repeating. P sub 3 is 1.4142, and if you've memorized square root of 2, or at least approximately memorized it, that's getting pretty close. What are we up to? Is that P sub 3? Is that what I said? P sub 4, P sub 5. Already by P sub 4 and P sub 5, they're the same to that many decimal places. Of course, if we carried more decimal places, they would be different. If you square that number, the calculator is rounding it to 2. It's keeping enough digits of accuracy to go ahead and round the square of that to 2. So essentially, I think it was just 4 iterations brought us to the root to, what would it be? How many significant digits? 10? 10 significant figures after just 4 iterations. That's pretty amazing. We're to within an error of, I guess, less than 10 to the negative 9 or something like that. 10 to the negative 8, I'm not going to worry about it. Somewhere in that ballpark, after just 4 iterations, we are that close. That's pretty amazing. Newton's method works really well. We'll also learn about, sometime in the next couple class periods, something called accelerated Newton's method. evidently, which is even faster. Whoa. That's the basic idea. Now we're going to use Mathematica for the rest of class to do various things, starting with Newton's method. I've got some code here, and I'll share this with you after class. I've been forgetting that sometimes, so if somebody could remind me, that would be great. I've got some code that you don't have to worry about this, how this works, unless you are interested, that I call Newton plot, that essentially creates a Mathematica function, your very own Mathematica function. It's a module, which is essentially like a subroutine. Has local variables like mylist. What's this function? This is the function g that we're iterating. By the way, I could have called that function g. I could go back here and label this thing g of p sub n minus 1. That's the function that we're iterating when we do Newton's method. So you can see that here in the code, G is being programmed into Mathematica here. Nestless is being used to generate the numbers, the iterations of G. Print evidently must show the numbers themselves. Plot is going to make a plot of the function. This epilogue stuff is a complicated way of making it do what I want to do. Essentially, draw the diagram that I drew for you by hand is what it's going to do. Don't worry about details. So here, with this example, we've got the function f of x equals x cubed minus 50. We're after a root. Evidently, that's going to be the cube root of 50. And what's that going to be? That's going to be between 3 and 4. Now that I've entered this code, I can use it. Notice the syntax. The inputs are the function f itself that you're trying to find the root of, a range of values for x, a range of values for y in the plot. The c, that's the initial guess, the number of iterates, and places of accuracy. I think sometimes this places of accuracy doesn't work the way you might want. Let's see what this produces. Okay, it is doing 10 significant digits, it does look like, with this 10 here. So there's our function f. The window you can see, x goes from -3 to 6, y goes from -30 to 80. You can see that in the graph. Phi is the initial guess that corresponds to this point here on the horizontal axis. 6 iterations, starting with 5. Yeah, we do see 6 iterations here. Getting by the 5th iteration to being correct to that many decimal places that you see. And you do see it in black here going up to the graph. This is the tangent line at this point. Find its x-intercept, go up to the graph again, find the new tangent line, find its x-intercept. We're already so close you can barely tell the difference anymore. Let's try some other examples. So here the function is 2x cubed minus 15x squared plus 24x minus 3. What happens in this example? Something bad happened. Complex infinity. What's that? Indeterminate. What's that? We must be dividing by 0. But the initial condition here, the initial seed is 1. What is f prime of 1 here? It's 0. Yeah, we're dividing by 0. So that's a bad seed to choose. If I choose something different, like 1.1, that, well, it's a different seed, but it's doing something weird, isn't it? It's going up to the graph, finding the tangent line there. The tangent line is close to horizontal, you might say, relatively speaking, and its x-intercept is way over here. And then we follow that curve. We're heading toward this root right here. So we're not going close to the root that we were, you might say, that we were after. We're going close to a different one. So definitely, if you're dividing by derivative value, that's 0, that's trouble. But even if it's close to 0, you may not converge to the root that you are hoping to converge to. Oh, I am also seeing why with this place of accuracy, it's sometimes not working. Mathematica as a default, if you put there a number in there as a decimal, it uses less places of accuracy. So if I wanted to get more places of accuracy, I want to put the 1.1 in there as about an 11/10. Yeah, now we're seeing more. Okay, so that's why it doesn't always work, so to speak. Question?
What's the 6 for?
The 6 is the number of iterations.
Oh,
How about this example? What's going to happen? Huh. We go back and forth between 1 and 3. Okay, these are very special examples. These things are not going to typically happen. Okay. But I'm picking these examples so that strange things can happen. And these do come up in your homework assignment, by the way, these exact same examples. So I'm previewing what you're already going to do, but you will need to give some explanation observing what's going on. What if I change the input, the seed here slightly from 1 to say 1.1? Now it does seem to be working, seems to be converging to that, although in an oscillatory way. That's kind of interesting. What if I picked a number less than 1? Then it's converging to something else. So the moral of the story here is unexpected things can happen. Here's a really weird one. What about this function? 4x minus 3 over x to the 1/3 power? What in the world? Errors. And what's happening? We're getting evidently complex numbers. Well, these imaginary parts are so close to 0, or you might say that's numerical error. It's actually the fact that Mathematica is being too fancy for its own good and trying to bring in complex numbers where it shouldn't. If you use cube root instead of 1/3 power, it does a better job, but it still is weird in that the iterations seem to go all over the place. We saw this a little bit last time. They're kind of chaotic. They're not seemingly converging to a root. Now, actually, the root of this function is very simple. It's just 3/4. So we know the answer already, but it's illustrating that if you don't pick a seed equal to 3/4, that we're getting chaotic behavior. Okay, so again, this comes up in your homework assignment, but I wanted to preview it a little bit before that point. You will need to give some brief explanations and descriptions about what's going on.